This discussion is going to be about Cantor's theorem. So this is stated right at the end of section 2.5 in the textbook on infinite sets. The theorem says that the power set of any set is bigger than the set itself. And your textbook sort of just states this, but it doesn't show you why it's true, and it doesn't show you why that matters. And so I have a few slides here to go through that will explain this. And here we go. So Cantor's theorem. First thing to be reminded of is some vocabulary about functions. A general function f takes members of one set, the domain A, and sends them over to a corresponding member of another set, the range. So in this picture, A is the domain and B is the range. And it's okay if two different x values get sent over to the same y value. So in this picture, I've taken, maybe this is x equals 2 and this is x equals 3, but they both go over to the y equals 3. Two different x's go over to the same y, and that's okay in a function. The important thing in a function is that each x has exactly one value of y that goes with it. F of 2 is just 3. There's not more than one different f of 2. It can't be ambiguous what f of 2 is. It has to be just one definite member of the range. That's a general function. Now, an injective function would not allow this f of 2 equals f of 3. In an injective function, each y has at most one x value that it comes from. So in our example with the general function on the left, y equals 3 came from two different x's. That's okay for a general function, but you can't have that with an injective function. Now, either way, whether you're a general function or this special type, this injective function, it's okay if one of the y values gets left out. You might have an extra element of the range B here that's not f of anybody. So you got an extra y value with no corresponding x, and that's okay for a general function or an injective function. But a surjective function cannot have that. Each y value has at least one x, such that y is f of x. So injective, y has at most one x. Surjective, y has at least one x. And bijective is just both. So each x has exactly one y, and each y has exactly one x. And that's a one-to-one correspondence. And why am I bringing this up? Well, our idea of when do two sets have the same size or the same cardinality, it's when you can find, or when there exists a bijective correspondence between the two sets, and you say they have the same cardinality. And Cantor's theorem is saying that a set and its power set do not ever have the same cardinality. Okay. So here's an example with a small set. Set A just contains 1, 2, and 3. The power set of A, that's the set of all the subsets of A. And I've listed them out here. There are 8 subsets of the set A. And so you cannot put A into one-to-one correspondence with its power set because the power set's bigger. They don't match up one-to-one. That's easy to see when you're talking about finite sets. Just to make it more formal, a finite set with n members has 2 to the nth different subsets, and that's bigger than n, so there's no one-to-one correspondence. So the cardinality of the power set's bigger than the cardinality of the set itself. When we're talking about a finite set, you can count the members, you come to a certain number, n. But if you can't count, what if you have an infinite set, like the set of all the natural numbers, 1, 2, 3, 4, going on forever, and you want to compare that with its power set? It's also infinite. So maybe it's the same kind of infinity, or maybe it's 2 different kinds of infinity. Depends on whether or not you can make the one-to-one bijective correspondence. Okay, so what if there were a bijection? So I've drawn some arrows here. I've just made something up. Said maybe 1 corresponds to the empty set, and maybe 35 corresponds to the set whose members are 1 and 2. And all I'm saying is maybe there's some way to go back and forth between the natural numbers and the sets of natural numbers. So each member of the power set is a set of natural numbers. Each member of the natural numbers is a natural number. The question is whether you can match those up. And what Cantor did was he found an element of the power set, a set of natural numbers he found, B, that cannot possibly match up with anything. And so there cannot be a bijection. So the 2 sets in the natural numbers versus the power set of the natural numbers have different cardinality. So what is this special set B that cannot match up with any n? I put an n question mark here. I'm wondering what could n be, and it's going to turn out there's not anything. N could not be anything. So Cantor found the very special set B that does not match up, the leftover element of the range. Okay, so even though I'm making up this f of 1 equals the empty set, f of 35 is the set containing 1, 2, etc., I'd made up a function, or part of a function. But you could make up lots of different functions. And what Cantor's saying is, for this set of B that he found, if f is surjective, there cannot be any number corresponding to it. So it can't, if it's surjective, it cannot be surjective. It's a contradiction. Okay. So, what is this set? Well, there it is. B equals the set of all x's in the natural numbers, okay? B is the set of all natural numbers x, such that x is not a member of f of itself. So remember, f, well, you give it a natural number over here in the domain, and f of that natural number is supposed to be some set of integers over here in the range. Well, b is one of those sets of integers. And the question is there any x over here in the domain so that f of x could be b? Now, if f is a surjective function, that means it must be f of somebody. That's what surjective means. So if f is surjective, there would have to be a number n over here so that f of n equals b. But now in the next couple of slides, I'll show you how Cantor proved, but n cannot be there. Why can't b match up with any element of n, of the natural numbers? Suppose there was a number, little n, belonging to the natural numbers that did match up. So f of n equals b. Cantor asked this amazing question. Is n an element of b or is it not? Cantor showed it couldn't be either way. You couldn't either have n as an element of b or n's not an element of b. Either way, you get a contradiction. So there's no such n. You say, if f was a surjective function, there would have to be such an n, but there's no such n. So f's not surjective. Now, I ask kind of a silly rhetorical question here. I say, well, do you see why you couldn't have either n belongs to b or n does not belong to b? And this is the part where Cantor was just really clever. Okay, it's short. The reason why is very short. We got two slides. One to show you why you cannot have n as belonging to b, and another slide that shows you why you cannot have n not belonging to b. It's just one of those things, you know, I'd never think of it in a million years. Hundreds of professional mathematicians would never think of it. Cantor thought of it one day. Of course, there's lots of things he never thought of, so, you know, but here you go. Why could you not have n belongs to b? Well, if n belongs to b, then n belongs to the set of all natural numbers x who are not inside f of themselves. How did Cantor get that? He just replaced the letter b with this definition of b from the previous slide. Okay. So if n is one of these numbers, it does not belong to f of itself. B is the set of the numbers that don't belong to f of themselves. So n does not belong to f of itself. Okay, well that means n does not belong to b. Why? Because at the outset, we're saying, what if there's a number n so that f of n equals b? Okay, so I just replaced f of n with b. So if n belongs to b, then n does not belong to b. That's a contradiction. Okay. Well, why is it also not true that n doesn't belong to b? Same kind of argument. Suppose n does not belong to b. Then n is not one of these natural numbers who doesn't belong to f of itself. F doesn't belong to f of itself. So n does belong to f of itself. Well, f of n is b, so n belongs to b. You see the contradiction. If n does not belong to b, then after 2 steps, n does belong to b. That's a contradiction. So, if f was a surjection, then this set B would have to be f of somebody, n. But n can't be anywhere because it's not in B and it's not in B. So there's no such n. So f's not surjective. So there's not a one-to-one correspondence between these two sets. So why does it matter? What's the conclusion? These two sets are two different kinds of infinity. You could replace the n, the natural numbers, with any other set S, and you can do the same argument. There's not any set that has the same cardinality of its power set. And that means you can make a chain. You can do the power set, and the power set of the power set, and so forth, and make bigger and bigger cardinal numbers. So this Aleph null is how many natural numbers there are. This Aleph 1 is how many sets of natural numbers there are. This Aleph 2 is how many sets of natural numbers there are. And so it goes. Now, it's been proven that the number of real numbers, all the possible distances, is Aleph 1, but the number of fractions is Aleph null. The number of points in a plane is still Aleph 1. It's thought that there's not any cardinal number bigger than Aleph null, but smaller than Aleph 1. So it's like there's no Aleph 0.5. That is believed, but it's not proven. And that's all for this lecture.